This video is about electromagnetic radiation. You should already be able to describe the light spectra and how it can be formed by excited electrons. In this video, you're going to be able to calculate the wavelength, frequency, and energy of waves. The questions of the video, for fun, was how did the Hulk become incredible? But realistically, how do we hear music on the radio from such far locations, and how are those waves different? So electromagnetic radiation is energy that exhibits wave-like behavior and travels through space at the speed of light. The speed of light is written on your reference table as c, and its value is 3 × 10⁸ meters per second. Because there are different types of energy, they have different wavelengths and frequencies that would govern the same speed. So if you look at the picture on the right, this is all going to travel in 1 second. Every time it goes up and down is considered a cycle. This red color is going through 4 cycles up and down. We call that 4 cycles per second, or 4 hertz. So it's however you want to think of your unit. In the second example, the green color is going up and down 8 cycles per second, or 8 hertz. That is your frequency of how many times it goes up and down. Again, down here, its frequency is 16. The frequency is denoted by the V-like symbol. The wavelength is the distance between the two peaks. So because this is going up and down less often, its wavelength is longer, because this is all occurring at the same time. Because it's going up and down more often, and its wavelength is much shorter. So as you can see, wavelength and frequency are indirectly proportional. So here's another picture of the electromagnetic spectrum. Radio waves have very long distances to travel. And in that case, they are not very energetic because they're not going up and down as much. So their frequency is very small. So long wavelength but low frequency, compared to other things that have frequencies in much higher hertz or cycles per second. But in that case, if their frequency is really high, their wavelength is really short. Things like gamma rays have very short wavelengths, but they're happening so often, their frequency is so high, their energy is really high, so they can penetrate smaller spaces. We can actually calculate the wavelength based on the frequency, or the frequency based on the wavelength, using the C = wavelength V formula on your reference table. It's pretty simple, you just have to plug the numbers in, but you also have to check to make sure your units are compatible. So if the wavelength is 650 nanometers, calculate the frequency of light. The first problem is the speed of light is in 3 × 10⁸ meters per second. And so this is going to run into a problem. If you just write 650 in the blank, it's not going to have a compatible meters to nanometers unit. So what you'll notice is I didn't change the base 650. All I did was, if nano means 10 to the -9th, I literally substituted 10 to the -9th in for the letter nano. Again, I didn't change the placeholders. It's 650 still. It's incorrect scientific notation. But it's not my right answer yet, so I don't really care that it's improper. I'm literally going to put in my calculator 3 × 10⁸ divided by 650 × 10 to the -9th to get my answer. Now it is incorrect scientific notation, so that's convenient. And it tells me what my frequency is. So it's going up 4.6 × 10 to the 14th cycles every second. That's pretty high frequency because its wavelength was relatively small on the nanometer side. Again, if the frequency is 200 per second, or hertz, calculate the wavelength. So we're going to go backwards. It still has the 3 × 10⁸ meters per second on the left because that's a constant. The wavelength is what we're solving for, and we put 200 in. This time the units are compatible, seconds to seconds, so all I have to do is divide, and my answer is 1.5 × 10⁶ meters. If I know how far something's going, I can figure out its frequency. If I have how many cycles it's going through, I can figure out its wavelength. Planck is a scientist who decided that matter can transform into energy, but only in packets called quantum. So there's packets of energy coming together, almost like moles of substances. And Planck found that these energy packets are in multiples of hv, which is Planck's constant, times the frequency at which they move. So the formula that you see on your reference table is a relationship between energy and frequency. In this case, again, Planck's constant is written on the reference table as 6.63 × 10 to the -34th joules per second, and it's a constant. So all you have to do is use that calculation to go from energy to frequency. Here's a type of question. Copper chloride in fireworks gives off blue light with a wavelength of 450 nanometers. What's the amount of energy emitted? So when you look at your equations, there is no calculation that takes you straight from energy to wavelength. So that means that this is a two-step problem. First, I'll solve an equation that does have wavelength in it. The same equation that we used first. So the speed of light, 3 × 10⁸ meters per second, And the wavelength will go here to solve for frequency first. So again, wavelength is 450 nanometers. That unit is not compatible with meters, so I changed it to 450, did not change that, times 10 to the negative ninth. Nano means -9, so I plugged it in as the nano, and solved for frequency. It is not my answer, because I didn't ask for frequency, I asked for energy, so I also solve the Planck's equation. I put Planck's constant in and multiply by my previous answer to get an answer of 4.4 times 10 to the negative 19 joules. Notice the seconds have canceled, and that's on my own unit is joules, and that makes sense because last year we calculated energy in joules. The thing is, the joule number is really tiny, 10 to the negative 19th, and that's because this is for one packet of light, one unit of the light. If I wanted to talk about how much energy would be in an entire reaction, I might need multiple packets of the light, just like multiple pieces of a particle, right? Multiple particles. Einstein stated that the electromagnetic radiation or light is a stream of particles called photons, kind of the same theory. And between the two, the light came up with like a wave-like idea, and that it goes up and down with their frequency and wavelength, but it's also somewhat particle-like, where if you kind of stop it, you can measure other instances of it. And because E equals hv, and V can be substituted as c over wavelength, you can actually plug the two equations together to say E equals hc over wavelength. This is not on the equation list because they think you can use each equation separately. But if you'd like to combine them and know that on your own, you're more than welcome to. De Broglie is another scientist, and he said if light is both wave-like and particle-like, can matter be both as well? So is there a possibility that matter comes in waves? And that is true too. He found that electrons, which are particles because they have a very insignificant, but they have a mass, they're so small that they wind up having a measurable wavelength. So yes, they do kind of cover in an up-down-like pattern, as we mentioned in the quantum mechanical model. So what we're basically saying is, and this is his formula that you won't have to really use unless you'd like to, that if your mass is very tiny, like electron, that makes this denominator really small. And if the denominator is small, that means that the entire unit is really big. So the smaller the mass is, the higher the frequency will go. Light is infinitesimally small, which is why it has a measurable wavelength. Electrons are much bigger than light, so that's why their wavelengths are much smaller. But as you get bigger, like a person, its mass is so big that the measurable wavelength is so tiny that it's almost immeasurable. So remember light, spectra, and Bohr, that energy was in these quantums or packets of light, and when the light was passed through a prism, you could see them come out in colors. And Bohr actually used that energy to create his quantum mechanical model of the atom, his Bohr levels, which we have broken down ever since. So again, that visible light is only a small part of our spectra. It only occurs here. Ultraviolet, X-rays, gamma waves, microwaves, infrareds, and radio waves are not visible, but are calculable. And these colored lights are seen because electrons are popping between not only just energy levels, as it's easier to understand as in Bohr, but also they're popping between these sub-levels from S to P to D to F. And so whenever they move from a high energy level to a lower energy level, they give off light in different colors, and they can be calculated using a formula. This formula is also not in the reference table because it will not be tested, but we're going to be using this formula to calculate the energy level in our lab. So I just wanted to show you what it looks like. Another constant divided by what level it's in. So if it's in level 1, it will be divided by level 1. 1 squared is 1. So it is that number. But if it's in level 2, it will divide by level 2 squared, which is 4, and it will get even smaller. At this point, you should be able to calculate the wavelength, frequency, and energy of waves.